Okay, so exam 2 is on Tuesday, 2/20, my 45th birthday. Thank you. I haven't made it yet. Yeah, exactly. And the topics are everything up through rigid body statics. So we won't even start the next section today. We'll just keep going with this stuff, and everything that we've covered so far is going to be on the test. And remember that it's cumulative, so you need to go back and remind yourself about how to do the old problems. Yep. No, it would just be problems like the assignments and like the last test and that sort of thing. So the problems that I assign are always supposed to be blueprints kind of for the problems you'll see on the tests. Statics, by the way, this class is so cumulative anyways, like even if it wasn't cumulative questions, stuff keeps building on itself more than I think any other class that I teach. So, all right, well, somebody asked me to do number 10, and I know I've been asked about that in office hours too, so let me start with that one. Okay, so this is the one that looks like this. Yes. There's a ball and socket joint here. There's a pulley here and another pulley here, and a cable goes through those and connects up to the wall. I'm going to be just like drawing this problem the whole rest of class. And this one goes over to the wall. And over here, one goes to the wall. And there's a force straight down of 140 pounds. And then we have a bunch of dimensions. So this is 136 inches. This is 100 inches. This is 48 inches. 44.8 inches. And then this is 72. And out to the end is 140. Okay, and I think that's everything we need to know. And so the joint with the wall is a ball and socket joint. It's a single cable that goes, oh, let me label these. So they call the points, this is A, right in the middle here is B, this pulley is C, at the wall is D, and then at the little cross part is E and F. And then the cable connections are G, and all the way on the other side H, and then I up here. And they give a coordinate system where the origin is here. So this is the positive y-axis. This is the positive z-axis. And that means the positive x-axis is like that. That drawing went better than last time I did it.
So just by looking, how could you tell the difference between like a positive and negative z? Is positive normally coming?
I think maybe my picture cut off the fact that it actually drew the positive z over there, but that's an important point actually. It doesn't come up as much in this class as in like dynamics and beamformers, but x cross y has to equal z. So if you use the right-hand rule to start in the x direction, curl your fingers towards the y direction, your thumb points positive z. Okay, so if you ever draw a coordinate system that doesn't have that relationship, you don't have a right-handed coordinate system, and everything's going to go haywire if you do vector stuff. Okay, well, let's start by figuring out the coordinates of all these points. So D is the origin. Well, that's just where all my axes are crossing, and the question did show that. But when I drew the coordinate system there, I specified that it had to be there. And then A, to get to the point A from the origin, you go 140 inches in the positive x direction, and then you're there. To get to B, oh yeah, you're right. 72, what's 120 minus 72?
No, these just
I just didn't want to mess up all the stuff that looks so nice. Okay, well, yeah, I'll put it here. I'll mess it up. Okay, so this is 120. And then these, I also didn't give these dimensions, but these are each 10 inches. From B to E and B to F, that's 10 inches in each one. Okay, so the point B is 120, 0, 0. The point C is 72, 0, 0. P is the origin. Okay, so E now. How do you get to E and F? So those, you can think of just going 120 inches out to B, and then 10 inches in the positive Z to get there, or 120 out to B, and then 10 inches in the negative Z to get there. So the point E is 120, 0, 10. And the point F is 120, 0, negative 10. And then for G, we're just starting at the origin and going 136 inches in the positive Z direction. And to get to H, from the origin, we're going 100 inches in the negative Z direction. So 0, 0, negative 100. And then the last one is I. That's just 44.8 inches in the positive Y direction. Okay, and I'm going to draw a free body diagram. Well, let's do that, and then we'll choose the about point from the free body diagram. Okay, so we're dealing with this shape. There's the cross piece that goes to E. There's the end. Here's the cross piece that goes towards F. And now we have to think about how we're going to treat the cable. So the cable that goes from I to C to F to H. Okay? We could include the pulleys here. We probably want to include the pulleys no matter what, because otherwise we have to deal with the fact that those pulleys make a fixed joint connection with this, and we'd have to deal. So we want to include the pulleys so that the only forces are cable forces. But notice something sort of annoying happens if we include just the two pulleys. We would have a force with a magnitude of T pulling that way on that pulley, and a force with a magnitude T pulling that way on that pulley, and an equal and opposite force pulling that way on the other pulley, and one going that way. These two, the cable force this way on pulley C and the one this way on pulley F, are equal and opposite. We'd just rather not deal with that. So I'm going to include this strip of cable in there. If you don't see that and do that, that's fine, as long as you could deal with those two cable forces and you get the same answer, but you just have two more things to calculate. So in my free body diagram, I am going to include this pulley and the cable that goes like that and that pulley. Can you see what I'm talking about there? You could also think of something like that. Okay. So as long as you can make a closed outline around it, you can isolate that. I have a closed outline there, so that's fine. And that's everything that we're isolating. So now we want to apply the forces. There's no weight forces. There's a ball and socket joint here. A ball and socket joint applies 3 components of force. So I'm going to call this RD. We have the downward force acting here of 140 pounds. Then from the cable, from the pulley at F, we have a cable force going this way. And from the pulley at C, we have a cable force going this way. And those are both the same cable. So I'm going to call that, I'll just call that T. And then on the other side, we have a different cable going this way, and I'll call that one TE. That's a different tension. Yep. So, right. So the force here and the force here have the same magnitude but different directions. And so to get the unit vector for this one, so first we'll calculate the vector that's in the right direction, which is I minus C. And then we'll divide that by its magnitude, and that'll give us the unit vector for this force. And then over here, and then we'll multiply that by T. And this one, we'll calculate the vector H minus F. That has the right direction, but isn't a unit vector yet. Divide by its magnitude, multiply that by T, and then those are the 2 force vectors. In the problem, I guess I will make a little note next to the rows in the table when I write the table out. Any other questions? Okay. So row, force, moment. First, I'll do that force RD. Row vector, since that is our about point. I didn't say that, but let's put the about point there. Row vector is 0, 0, 0. Force vector is the components of RD. Cross product is 0, 0, 0. And then we'll do let's do the cable force that goes to I from C. So I'll just call that, I don't know, FIC or something, just something to reference it. The row vector, where does that force act? What letter does that force act at? It acts at C, so the row vector, notice since our origin was at our about point, all of these row vectors are just the coordinates of the place where the force is applied. So that row vector is just 72, 0, 0. And now we need to calculate that unit vector. So to calculate force FIC, a vector in the correct direction is I minus C. So 0, 44.8, 0, minus 72, 0, 0. And so that U vector is negative 72, 44.8, 0. And then can someone calculate the unit vector in that direction? That's the force vector going to I from C. It's just to help me differentiate between the force along this line and the force along the line HF. Not the unit vector wouldn't be, because 0.849 negative, and 0.528 and 0. Okay, and so that means that the force vector FIC is this unit vector times t. So negative 0.849 t, positive 0.528 t 0. Okay, so that's the force. So I'll put that in here for the force. 0.849 t, 0.528 t 0. And then what's the cross product? Well, it's just 72 times 0.528. .02t, is that what you said? Okay. And then the other force vector with a magnitude of t is the force going from F to H, or to H from F. So I'll call that the force vector HF. That force vector is acting at F, so the row vector is 120, 0, negative 10. And now we have to figure out the unit vector in that direction. So the force of the cable going to H from F, a vector in the right direction is H minus F. So H is 0, 0, negative 100. And F is 120, 0, negative 10. So a vector in the correct direction is negative 120, 0, negative 90. And then what's a unit vector in the direction of that? Yeah. 0, negative 0.6. So then that force vector is this unit vector times the magnitude, which is t. So force HF is equal to negative 0.80 t, 0, negative 0.60 t. So put that in the force vector spot. Negative 0.80 t, 0, negative 0.60 t. And then the unit vector is yeah, the cross product of this and this. 0, 80t, 0. And oh, the signs. Okay, so be careful with the y. Well, no, these signs are right. With the y, we're going to cross out the y. So this times this minus this times this, and then take the opposite. The easiest way to do it is to have it programmed into your calculator, and then you don't have to think about it. But, okay, so that's right. There's two more forces. Now we have to deal with this force TE, the other cable. That's acting at the location E. So the row vector is 120, 0, 10. And now we have to figure out what that force vector is. A vector in the correct direction is G minus E. So 0, 0, 136. Minus 120, 0, 10. And you get negative 120, 0, 126. And then what's a unit vector in that direction? 6, 8. 6, 9, 0, and then 0.724. And the magnitude is TE. So this force is negative 0.69 TE, 0, positive 0.724 TE. And now put this in the force in that row. Negative 0.69 TE, 0, positive 0.724 TE. And then what's the cross product for that? Okay, and don't forget the TE, 0. And then the only force left is that 140-pound force. The row vector is 140, 0, 0. Force, it's in the negative y direction, so 0, 140, 0. That's negative. And so you get 0, 0, what's 140 times negative 140? 19600. Okay. Looking at this, can you see Okay, well, let's count up the variables, count up the equations. Variables, we have 1, 2, 3, 4, 5. That means that one of our 6 equations that we get has to be useless. Otherwise, we have an overdetermined system. Can you see what? So these 6 equations, 3 equations come from adding up these components and setting them equal to 0, and 3 come from adding up these components and setting them equal to 0. Can you see where that useless equation is going to come from? The x component of the moment equation says 0 equals 0. So we have 5 equations, 5 variables. That's good. All right, so Newton's second law. Newton's second law says RD plus negative 0.849 t positive 0.528 t 0 plus negative 0.80 t 0 negative 0.60 t plus negative 0.69 te 0 0.724 te plus 0 negative 140 0 is equal to zeros. And the moment equation, I'm going to skip the x components and just do y and z. So we get 0, 38.02 t plus 80 t 0 plus negative 93.77 te 0 plus 0 negative 19,600 is equal to zeros. And those are our 5 equations. So let's solve this. So we need a 5 by 6 matrix. R dx, R dy, R dz, t, te, and constant. So equation 1, R dx's we have 1. T's we have 1.649. You have to add both of those two up. That's negative 1.649. TEs we have negative 0.69 and no constant. Equation 2, our dy's we have 1. T's we have 0.528. And the constant on the other side is 140. Equation 3, our dz we have 1. T's we have negative 0.6. TEs we have 0.724 and no constant. Then for the moment equation, T's we have 80. TEs we have negative 93.77 and no constant. And then for the last equation, T's we have 38.02. And the constant when you move it to the other side is positive 19,600. Everything I didn't fill in is 0. And will a few of you at least take a minute and solve this, and we'll keep going until 2 people's match. Mm-hmm. Okay. 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 These are all newtons. Oh, no, they're not. They're all pounds. Don't go through the whole calculation and then give the numbers to your boss in the wrong units. Apparently, I think this is true. Like the first thing that they tried to send to Mars failed. They got it all the way to Mars, and then they were dropping this little pod down, and it was supposed to lower itself down until these feet felt that it hit the ground, and then turn the rockets off. And this calculation had been done in newtons instead of pounds, or vice versa, and it felt a force of air resistance. And since it used the wrong units in the calculation, or interpreted as the wrong units, it thought that was enough force to feel to shut off the jets, and so it got to within 100 feet of the surface of Mars, and then just dropped itself and smashed on the ground. Yeah, exactly. Yeah, exactly. So don't do that. Yeah. Yes, exactly. Okay. Any questions about this? I would recommend, it seems like the way I did it, there were a lot of extra steps. We wrote a lot of stuff down multiple times and whatever, but I'm not going to make you rush to do this on tests. I'd say just take your time, be systematic about it, write out the table, write out the equations, write out the matrix. And yeah, if you think about it as just systematically, all these problems start to be pretty much the same thing, you know. Any other homework problems, particularly that anyone would like to see? Number 12. Okay, let's do this one. This one has one little wrinkle that we have to deal with. So number 12. So this one has a long beam that's connected to the wall by a pin joint. And there's a pulley that connects a cable going this way and a cable going this way. And those connect to the wall. And then there's a little slider that with a force acting down on it, and the magnitude of that force is given as F. So we don't have a number for that, but we're treating it as if it is a number. Okay, that's the parameter that this problem's based on. And the idea here is that if you're trying to design this thing, you don't know yet what this is attached to some other machine or some other part of the system. You haven't been given this information yet. Okay, but you want to figure out what these forces are in terms of this F. So our answer is going to have F in it, and then the idea is that when you get this new information that force is, okay, now we know that force is 500 newtons or something, then you just plug that in for F and you have all your answers. So we're going to treat that F as if it was 100 or something, you know. In other words, when it's a constant, we're going to move it over to the right side of the equation in our matrix and solve in terms of that. Okay, so these are both along the same line here. Okay. This looks pretty out of whack, but so this is given as 4 feet, and this is a lot more, right? Nope, that's 4 feet too. And then this is 5 feet. And then from here to here is 5 feet. And from here to here is 5 feet. And from the end to where the pulley is 2 feet. And the coordinate system has the x-axis this way, the y-axis straight out, and the z-axis up. Okay. Geometry-wise, if you look at this directly from the side, so here's the beam, and you have this cable that connects to the end. You would see a pulley there, and it would just be a straight line from the pulley up to the connection with the wall. Okay, so what do we know? We know that this is 5 feet. This is 10 feet. And so we know that this little triangle is a similar triangle to the big one. So this we're given is 2. That means this little thing here has to be 1. Those two sides have to be in the same relationship. Okay, and label these points. We'll call this, the origin is A, the end point is B, the cable wall attachment in the negative x direction is C, one in the positive x direction is D, the pulley is E, and those are all the forces. But notice we can use the length of this triangle here to figure out the location of E. Okay, so let's figure out all the coordinates. A is the origin. B is 10 feet in the positive y direction, so 0, 10, 0. C is 4 feet in the negative x direction and 5 feet in the positive z direction. So -4, 0, what did I say, 10, 5. D is 4 feet in the positive x direction, 5 feet in the positive z direction, so +4, 0, 5. And then E well, we know that the horizontal distance from the end to here is 2 feet. So if you go 10 feet in the y direction to get here, then you have to backtrack 2 to get here. Okay, so that's going to be 8 feet in the positive y direction. I'll write that first.
Is that 2 feet and like in the future if you see something like that,
Mhm.
that means it's not the length of the cable, it's
That's right. That is what a notation like that will always mean. You see how the it it did it like this, not exactly the way I drew it, but it drew the arrows like this. And what that means is that is a distance along the line parallel to those arrows. Okay. And then we have to figure out where it is in the z direction. Well, we just have to go 1 foot up from the y-axis. So that's positive 1 for z. So this vector is 0, 8, 1. And now draw a free body diagram. Okay, so there's all of that. And I think the easiest way to go in this case is to also include the cable that's attached there and the pulley there. So our free body is going to be something like this. Then we have a cable force like that with a magnitude T, a cable force like that with a magnitude T, a downward force F, and then this is a ball and socket joint at A. Oh, I'm sorry, that I misspoke before. That's a ball and socket joint. And I'll call that RA. Yeah, you could just call that R. That's hilarious. You're a ventriloquist. I'm not even listening. Okay, yes. I wonder if I do that in all my classes and just no one's ever mentioned that before. I'm just going to, like, how can you ask that? Okay. So row vector, force vector, MA. The about point, again, is going to be the origin. So for the row vector, we can just use the coordinates of these points. So the row vector to A is 0, 0, 0. The force vector is RA, X, Y, and Z. Cross product is 0, 0, 0. Then the force F, that acts at, oh, well, we don't even have a, well, so the location of that force is not one of these. It's 5 in the positive Y direction and nothing else. So 0, 5, 0. Force vector is in the negative Z direction with a magnitude of F, so 0, 0, negative F. And the cross product is negative 5f for x, and then 0, 0. And then we have two of those cable forces. So they both have the magnitude t, but one goes to d and one goes to c. So I'll call this FD is the one that goes from E to D. Vector in the right direction is D minus E. So U is equal to 4, 0, 5 minus E is 0, 8, 1. And so the vector is 4, negative 8, 4. And then the unit vector, oh, I've seen this one before. It's like, oh, I was going to say that. Okay, so the unit vector is 0.408, negative 0.816, positive 0.408. And so that force vector FD is this times the tension T. And then the other force vector I'll call FC. So the U vector is going to be C minus E. So negative 405 minus 0, 8, 1 is negative 4, negative 8, 4. And so the unit vector is negative 0.408, negative 0.816, positive 0.408. And so FC is negative 0.408 T, negative 0.816 T, positive 0.408 T. Now I have to put these two in the table. Both of these are acting at the point E, so the row vector is 0, 8, 1. The force vector FD is 0.408 T, negative 0.816 T, positive 0.408 T. And the cross product, can someone calculate that? What's the third one? Okay, P. And then the other one is acting at the same location, 0, 8, 1. The force vector is negative 0.408 T, negative 0.816 T, positive 0.408 T. And that cross product must be similar in many ways. So 4.08 T, negative 0.408 T, and then This one's negative again? Positive. 3.264 t. Okay, so variables. What? Oh, yeah. Yeah, t is definitely one of the variables. Let's see, we got 1, 2, 3. And then t is the fourth one. What about that f? This is where it can easily get confusing. That f is not a variable. That f is going to show up in our answer. We're treating that like that's a number. Okay, so the only variables we have are the vector RA and the variable t. And so, yeah, our answers are going to have f in them. That's a parameter that this problem is based on, so not f. And how many equations do we add? So hopefully 2 of these 6 equations go away. Yeah, so at first it doesn't look like it because you don't see zeros all over the place. But notice that when you add up the y components of the moment, you have a plus 0.408 and a minus 0.408 that cancel each other. And same thing with z. 0, 0, this negative cancels this positive. And so the only useful equation that we're going to have for the moments is the x component equation. All right, so Newton's second law says R A X R A Y R A Z plus 0, 0, negative f plus 0.408 t negative 0.816 t positive 0.408 t plus negative 0.408 t negative 0.816 t positive 0.408 t is equal to zeros. And then the moment equation, only the x equation is useful. And it says negative 5f plus 4.08 t plus 4.08 t is equal to 0. Put this into the matrix. So it's going to be 4 by 5. Equation 1, 2, 3, 4. And then the variables are Rax, Ray, Raz, t, and the constant. So yeah, Rax is just going to be 0. Yeah, well actually let's, you know what, now that I think about it, if you ever have a problem like this where you have to solve this solve for a parameter or solve stuff in terms of a parameter, it's always going to be reasonable to solve it by hand. And that's because they don't know if your calculator is cool enough to deal with it as the variable f. Some of yours are and some aren't, you know. So I'll set it up as a I'll set it up as a matrix, but I'll also just do it by hand. Anyways, for the matrix, I'm just gonna enter these all in, but RAX, we have 1, T's, we have 0, everything else we have 0. So RAX is just gonna be equal to 0. In the second equation, RAY, we have 1. T's, we have negative 1.632, and the constant is 0. Z's, RAZ, we have 1. T's, we have 0.816. And now F, we're treating that as a number, so that's positive F, goes in the constants. And then the fourth one says T's, we have 8.16. And F's on the other side, so 5F. Okay, so I guess there's a couple ways you could do this. If your calculator will let you use this with variables, and a lot of them will, then you can just punch this in this way and it'll give you an answer in terms of F. If you notice that all of the constants are multiplied by F, like you can think of that last column as just being the numbers 0, 0, 1, 1, 5, all multiplied by F, then you can just do this as 0, 0, 1, 5, and it'll give you the right answer. You just have to multiply all your answers by F. But you can also just solve it by hand. So let's see. I think you can. Can you? So RAX is 0. T is equal to 5F divided by 8.16. What's 5 divided by 8.16? 0.613F. And then RAY is 1.632 times T, which is 0.613F. So what do you get for that? One? Huh, that's interesting. F. Yeah, so that's just F. And then RAZ is F minus 0.816T. And T is this. .5. Okay. So now when people come to you later, you solve this problem, people come to you later and say, like, are we gonna go over the loads that are allowed if this thing if this force F is increased to, 1,000 newtons or whatever, and you have the formula right there that tells you. That's the idea. Any questions about that? Yeah. Mm-hmm. Okay, that's it. So test on Tuesday. I have an office hour on Monday from 11 to 12 if you want to talk about stuff before. Oh, you're right, I don't. So send me emails if you have questions. No, I'm definitely not doing that. Okay, enjoy President's Day.